So now we're going to get back to the main problem of statistics. And if you recall, that is that we have some population. So we have a population, and the form of the population is, say it's a function px, or maybe I should use this blue, it's px of x, okay? And this, remember, we are sticking to the case of independent, identically distributed random variables, so it's going to be in this product form. And this, of course, is our population. Okay? But here we say, well, what is the aim of statistics? The aim of statistics to infer properties of the population via some measured samples. Right? So we somehow want to take the samples, so we want to take the samples, we want to treat them, using, if you like, the tools of statistical inference. And on the right, what we want to pop out are essentially the information, let's say properties of the population. And we have a name for these properties. These properties, we call them parameters. So let's just kind of carefully say what we mean by parameters. So parameters, so let's just carefully say what we mean by parameters. So parameters, the parameters of the population. And again, this is some kind of vector because there could be more than one. This is A with an arrow over it. Well, this is a vector containing A1, A2, and up to some arbitrary highest value. So the parameters of the population, and these are the A, the AI. Well, these are real numbers. Let's say these are variables upon which the population depends. And in the context of statistical inference, we really do like to make this dependence very, very explicit. Okay, so we want to write the population in a way that shows that we understand it depends on these parameters and not just the samples. And the way we do that is by writing px of lowercase x, but not just lowercase x. We say given the samples A. Okay, and here we want to just be a bit more careful. So we're going to say given these samples A, we're going to say x given A, where of course these are the definite values of the parameters, and that capital A just is something kind of like the actual parameter itself. And we say this is equal to, well, it's P of x1, and we say given A times P of x2 given definite values of the parameters, dot, 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 all the way up to P of xn given definite values of the parameters. So all we've done is written the population in a way that makes it absolutely explicit that that our population depends on these parameters. Okay. Now, again, you might have wondered kind of why we've kind of written it this way. Well, now we're going to take up the idea of estimating these things. Okay, so here we're going to introduce another concept, the concept of an estimator. An estimator. Well, what is an estimator? Now, if we maybe just say a little bit carefully what an estimator is. An estimator is a function of the data items. And let's give it a symbol. We're going to say a hat of capital X. And notice I've said the data items, I said the data items, and I didn't say the samples. I was very, very careful about that. That is because really this function of random variables is itself a random variable. And we'll come back to what that means in just a moment, but an estimator is a function of the data items, and we say it is designed to estimate the true value of the parameter, A. Okay. Now, again, let's just come back here. Well, here you will notice that I talked about this capital A, which is a random variable, and lowercase a. I wouldn't worry too much about that right now. The only thing I'm going to say about that is that in the context of frequentist statistics, where we'll spend most of our times, this is kind of inconsequential because the parameters have definite values, and we can say that formally by designing a very, very sharply peaked probability distribution for A to follow. But again, please forgive me if I drop that bar A there, because really most of the time when we're talking it doesn't really make a difference. But in the Bayesian framework, formally these parameters themselves are random variables, and we'll have more to say about that later on. Okay. So an estimator is a function of the data items designed to estimate one of the parameters of the distribution. And we're saying, remember, we say it depends on these data items. So we say an estimator is a random variable. And before we said the data items are themselves random variables, so they follow some distribution function. Well, these estimators, they depend on those data items, so they're also random variables, so therefore they must follow their own distribution function. And what distribution function do they follow? Well, it's not called the population this time, it's called the sampling distribution. So the sampling distribution. Again, it might seem like a lot of words we're introducing here, but I promise we're almost at the end of definitions. But the sampling distribution is the distribution function followed by a particular estimator A hat, I'm going to again make it explicit that it depends on these data items, and it's an estimator of the parameter A hat, just A. Okay. And this is a parameter of the population, of course, so I want to be very, very clear about that. And the sampling distribution has a form, so we're going to say P, uh, bracket, well, let's kind of use blue, so we're going to say P A hat given A. So this is the value of the estimator given the true values of the actual uh, parameters. So we're saying suppose these have actual values, what would this look like? And well, there's kind of a way we relate this to the population. So we relate this to the population by saying, remember, these things are continuous. So this is a density function. So this is the probability that, this estimator is equal to this particular value, A hat. And this is going to be equal to the population. So this is population X given A, and note we've omitted that bar capital A here, like we said we might start doing. But this here, this is dx1, dx2, dot, 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 dxn. And this is a volume element that we're going to just comment very carefully on because it's a particular volume element. And essentially, this is the volume element that traps all the values of the samples that would manufacture this particular value A hat for the estimator. So what do I mean by that? What this means is that this volume element is the infinitesimal surface between, let's say that not infinitesimal surface, the infinitesimal volume between the surfaces. So it's between two surfaces, and this is the surface that A hat as a function of x is equal to this particular value A hat, and another surface A hat of x plus dx is equal to A hat, or well, let's just be a bit more careful about this. It's A of x is equal to A hat plus d A hat. Okay, so again, I just want to stress I want to be very, very careful in what I'm saying here. This is between these two surfaces. A of x is equal to A hat, and A of x is equal to A hat plus dA hat. Okay, so all of those values are going to be accounted for here. I should be a bit more careful about how I talk about this volume element here, but the point is, when we need to, it will be a bit more obvious what we're kind of doing. So I'll just kind of box this up. And again, I'm not going to really make many more comments about this right now, other than just to say, look, essentially, I'm saying, suppose we know the form of the population. This equation gives us a way to work out what the sampling distribution is. Okay, so this is really a relationship between the sampling distribution and the population. And even if you can't quite picture what this means, what's actually happening here, all I want you to try to understand is that the population is the distribution function for these data items, and any estimator is a function of the data items. So therefore, there's a sense in which I have to be able to say, if I know the functional form of my estimator, and if I know the functional form of the population, I should be able to work out the probability distribution for my estimator.